Hello, future engineers. Welcome to my YouTube channel. If you find my videos helpful in your studies, please don't forget to share them to your friends and to your friends. And to keep me refreshed, energized, and inspired. And if you like what I'm doing, don't forget to subscribe. By three-moment equation, analyze the continuous beam shown below. Also construct the shear and moment diagrams and sketch the elastic curve. EI is constant. So here is the given figure. So we take note that moments at A and at D zeros. Supports are unyielding and EI is constant. So we begin writing three-moment equation on span ABC. So moment at A 0 plus 2 times MB quantity 6 plus 5, then plus M sub C times 5. The value of 6 area 1A over L1 is, there's no direct formula, so you can have this by the long method, constructing the shear and the moment diagram by parts, or the shortcut. So we applied the shortcut because I already gave you enough examples for the long method. So we have here the strip, the area is 24 dx, so dp is 24 dx, and let's call that distance x from the left end of the load, variation of x 0 to 4. So that's 24 dx, and the value of 6 area 1a over L1 is dp times a, which is 2 plus x over L, 6 quantity 6 square, minus 2 plus x quantity square in integral form. So plus integral 0 to 4 of 24 dx times 2 plus x over L, 6 quantity 6 square, minus 2 plus x quantity square. Then the value of 6 area 2b over L2 is just 40 times b, which is 2 all over L5 quantity 5 square minus 2 square. Then equals 0 because the supports are unyielding. The value of the integral is 1024. The value of this is 336. Simplifying, we have 22 MB plus 5 MC equals negative 1360. Call that equation 1. We then write three-moment equation on span BCT. Note that moment at D0. So we have MB times 5 plus 2 times MC quantity 5 plus 4. Then plus 0 plus the value of 6 area 1A over L1 for span BC is just 40 times A, 40 times 3 over 5, quantity 5 square minus 3 square, while the value of 6 area 2B over L2 for span CD is we need to have another strip, and call this X from the zero load. Then W as to X equals 30 over 3. 30 over 3 is 10, therefore the height is 10x. Therefore dP is 10x dx. And therefore this distance is 3 minus x as our B. So 6 area 2B over L2 for span CD is integral of 10x dx. B is 3 minus x over L4 quantity 4 square minus 3 minus x square, limits of x is 0 to 3, the length of the load, then equals 0. The value of this is 384, while the integral is 149.625. So simplifying, 5 MB plus 18 M sub C equals negative 533.625. Call that equation 2. Then solve equations 1 and 2 simultaneously. We get MB equals negative 58.792 kilonewton meter and M sub C equals negative 13.315 kilonewton meter. We then apply the reactions RA, RB, R sub C, and R sub D. And the moments, since these are negative, clockwise to the left, counterclockwise to the right. So 58.792, same is true at C, 13.315. So for span AB, considering AB, we sum up moment about B, 0, we can solve for RA. So RA times 6 plus 58.792 equals moment of the load 24 times 4 times 2. So RA is equal to 22.201 kilonewtons. Then shear at B just to the left, downward positive, remember the sign convention. So it is just upward when it's downward for the forces on AB. So shear at B just to the left is RA 22.201 minus 24 times 4. So shear at B just to the left is negative 73.799 kilonewtons. While shear at B just to the right is upward positive. So we consider BC, we sum up moments about C, 0. So shear at B just to the right times 5, then plus 13.315, then equals 58.792, plus moment of the load 40 times 2. So shear at B just to the right is equal to 25.095 kilonewtons. Now that we have found shear at B just to the right, reaction at B is shear at B just to the right minus negative 73.799 because it changes from negative 73.799 to positive, so it should be upper minus lower. So it is equal to 98.894 kilonewtons. Then for shear at C just to the left, which is downward positive again, it is shear at B just to the right minus 40. So shear at C just to the left is 25.095, shear at B just to the right minus the only downward load is 40. So shear at C just to the left is negative 14.495905 kilonewtons. Then for shear at C just to the right, we consider CD and sum up moments about D equal to 0. So shear at C just to the right, it is upward positive times 4, then equals 13.315 plus moment of the load 1/2 or 0.5 of 3 times 30, moment arm is 1 moment arm. So shear at C just to the right is equal to 14.579 kilonewtons. Then reaction at C is 14.579 minus negative 14.905. So just compute it directly. You just add this, take this as absolute value, 29.484 kilonewtons. Then shear at D just to the left, which is downward positive, and the absolute value of that is equal to RD because there's no more support. So shear at D just to the left is shear at C just to the right, which is 14.579 minus the area of the load, which is 0.5 of 3 times 30 or 1/2 of 3 times 30. So shear at D just to the left is equal to negative 30.421. So reaction at D is positive 30.421 or upward. Or 0 minus negative 30.421 is 30.421. So these are the results. So on the next slides, we prepare the shear moment diagram. It will not fit here. The space is very small. Anong na-post na? So let us continue. This is the figure and this were the results in the first slide. So we then apply the reactions, prepare the shear and moment diagram. So RA 22.201, RB 98.894, R sub C 29.484, and RD 30.421 kilonewtons. So we begin with shear 22.201. So that's 22.201 constant from here up to here. Then minus 24 times 4, it goes down. And the ordinate here is negative 73.799, which is the shear at B just to the left. You check it. Then plus 98.894, you'll get 25.095, shear at B just to the right. Then constant up to the load. Minus 40, 25.095 minus 40 is negative 14.905, constant up to just to the left of C. So check shear at C just to the left is negative 14.905, which is correct. plus 29.484 is 14.579, which is the shear at C just to the right, 14.579, constant up to this zero load, and minus the area of the load, which is 1/2 of 3 times 30, uh, negative increasing rather, so we get negative 30.421, which is the shear at T just to the left, and plus 30.421, reaction at T that closes the shear diagram. Then for the bending moment diagram, we have from 0 plus 22.201 times 2, that's 44 point something. So first, let's solve for this distance x1 and this distance here x2 from the zero load. So shear AB is 22.201 minus 24 times x1, area which is 24 times x1, equals 0 because we want to find x1. Shear here is 0. So x1 is equal to 0.9250, or the other way is you apply similar triangles and you'll get the same result. But the technique is you write shear equation for from here up to B, which is shear 22.201 minus the load, which is 24 times x1, 24 times x1, and equate to 0. So 0.925. Then area 1, this area is just an area of triangle, so I will not show it anymore. Then let's have x sub 2. The shear in portion from this point, I'll just call it CD, although it begins with this 0 end for 3 meters only. So we have a strip and call this x2. x2 begins from this 0 end up to this strip, so which is for the 3 meters length. Then this was 10 x2, or 30 over 3 equals W as to x2. So this is 30 x2. 30 over 3 is 10 x sub 2. So the shear for this portion is 14.579 minus the area of this triangle, which is 1/2 of x2 times x, 10 x2, and we equate it to 0 because we want to find x2 where shear is 0 here. So solving for x sub 2 is 1.7076 meters. So we'll call this area 1 and this negative area as area 2. Let's compute that later. So now this time integral of shear dx2 from 0 to 1.7076. So this is the shear equation for from this point to that point. Limit 0 to 1.7076, 0 to x2. And the area 1 is equal to 16.596 kilonewton meter. The other way, because it begins with zero load or zero tangent, horizontal tangent here. So this is a parabola, area 1. Area of parabola is 2/3 x2 times height, 14.579. So area 1 is 2/3 of x2, 1.7076 times height, 14.579. So area 1 is also 16.597. The very small discrepancy of 0.001 is due to rounding off. So we'll just accept 16.596. Then area 2 is same shear equation, same integral, except the limits 1.7076 to 3. Because x2 begins with the 0 and not at C. So area 2 is integral from 1.706 to 3 of same shear equation dx2. So area 2 is negative 17.859 kilonewton meter. So we then plot the bending moment diagram. It begins with 0 moment at A, then plus 22.201 times 2, so 44.402, straight line up, 44.402 plus the area of this triangle, which is positive decreasing, so like that, concave down, but rising. So 44.402 plus 1/2 of x1 times 22.201, that would be, use your calculator, 54.67. Then minus the area of this triangle, which is 54.67 minus 1/2 of 4 minus x1, 4 minus 0.925 times 73.799 from zero slope, negative increasing. So the value here is, check with your calculator, negative 58.796, which is supposedly the moment at B. The moment at B is negative 758.792, so the small discrepancy is due to rounding off. So that's acceptable, 0.004 difference. Then plus the area of this rectangle, which is 25.095 times 3. So negative 58.796 plus 25.095 times 3. It traces straight line first degree because that's 0 degree. So the value is 16.489, and minus this area, which is 14.905 times 2, it goes down to negative 13.321. The expected moment at C, which is, this is supposedly a moment at C, is negative 13.315. Again, the small difference is due to the rounding off of this value to 3 decimal places only. So if we round that off to 4 decimal places, the results would be very, very close. In fact, these are already very, very close. Then plus area of rectangle, which is 14.579 times 1, so plus 14.579, negative 13.321 plus 14.579 times 1 is positive 1.258. Then plus the area 1, which is positive, so positive decreasing again, just like this curvature here. So 1.258 plus area 1, which is 16.597, is 17.855. That's the maximum for this span, positive moment. But the maximum moment is negative 58.792. The positive moment is on this 54.67 on span AB. So 17.855 plus area 2, which is negative 17.859, is almost 0. So the difference of 0.034 is understandable. So that closes the moment diagram. We then project these 0 moments. These are the points of inflection where concavity changes from concave up to concave down, or concave down to concave up, vice versa. So let's project them upward. This portion is positive moment, so it is concave up, positive curvature, concave up, or y double prime is positive. Then from concave up to concave down, this is concave down through the supports. Remember, elastic curve passes through the center of the supports. Then concave up again, concave down, and concave up for this portion, positive. So the elastic curve looks like that. So again, what is important is the curvature. But for obvious loadings, the elastic curve should be clear. For obvious loadings like this, it should be below the horizontal axis. But here, if you cannot anticipate that it is above, so as long as it is concave down for this portion, that's acceptable. But the correct or accurate way is you solve like deflections at representative deflection at each span of the beam, but that's a long method. That's only true for long tests or quizzes in the school where the time is enough. But for this presentation, what is important is you know how to apply the 3 moment equations and the construction of the shear moment diagram, as well as the sketching of the elastic curve. So that's it.